Log on, tune in, find out. Another good idea from Cambridge.
So now, I know that Pierre Druilhet has been doing work on crossover designs for many years, and while he's been here, he's been doing some work on optimal crossover designs for full interaction models. So Pierre, over to you.
Okay, first I want to thank Rosemary for having invited me to this program. And so I will present some work I am doing now. Not yet completely finished, but...
When do you leave?
Well. So first, the first part is an introduction, which is in fact a continuation of a discussion that we had with Rosemary and Joachim about what is a crossover effect and what should be the effect of interest. First, I present quickly what is a crossover design. So you have several subjects, or for field experiment several blocks, and you have several periods or plots. And for each subject you apply a sequence of treatments. And you are interested in the effect of the treatment. So the problem is what is the combination of sequence you have to put in the subject to obtain an optimal design. So a crossover design is a design with T treatment to be compared, N subject, K periods, and usually you assume that there is a large variability between subjects, and you want to reduce this variability by putting several treatments on the same subject. The problem is that this way to do the thing may induce a carryover effect. So this may be a problem in the design or not. It depends on the cases that we will discuss later. And usually we want first an efficient block row column design. For example, balancing completer design, Latin square, which has some neighbor balance properties. Usually the related model is an additive model that you assume that the response on the subject I and period J is the sum of a block effect, a period effect, a treatment effect of the DIG is the treatment applied to the subject I on the period J, and a carryover effect, which is a residual effect of the treatment which was applied in the previous period, and some errors that we will assume uncorrelated and with a mean 0. So in vector notation you have this expression here with B, P, T and L as the corresponding matrices of the effects. But the problem is that this model is often too coarse to be used in practice. For example, if I take a two-period design, it is well known that there is some confusion of effect if there is some carryover effect between the first period and the second period. So this kind of design is usually very not efficient, because mainly to estimate the main effect you use the first period, and you have a large variability of subjects that appear. So you cannot use this kind of design with the model of with carryover. So usually you put a washout period. That is, you want to eliminate the previous the effect of the previous period. So the washout period, you apply no treatments, and you have some baseline, and then you apply the treatment. So in that case, you eliminate carryover effect. So you have just row column design. And in that case, you are interested the effect of the treatment, but which is preceded by nothing before, by a washout period. So that's the problem arises: what is actually an effect in a carryover effect? The two main domains to where this kind of design are applied is the sensory analysis, where Joachim is a specialist, and also drug experiments, especially for chronic disease. For sensory analysis, when you try a new, for example, new wine or new food, the first impression is not always the impression that to be considered, because if you try once, you may be surprised, and it's just at the second or third time that you to have a good impression or bad impression or good impression. It's the same thing for a movie. If you see a movie for the first time, you are impressed by special effects, for example, and if you see the movie a second time, then you maybe you see more about the scenario, and so the expression may change. For example, for Steven Spielberg, for Stanley Kubrick movie 2001: A Space Odyssey, he said that he appreciates the movie after the seventh time. So it may be also the last impression. That means if you are when you try several times food, for example, the last impression is that that's impression that will decide if you will buy another one this item or not. In drug experiments for chronic disease, well, the actually important effect is a treatment, a drug which is taken constantly, continuously. But when you have a treatment, you use every time the same treatments. So this is the main effect that to be considered. But you can also be interested in the effect of the treatment just after the first period. For example, if you have some pain disease or after surgery, something you have to take drug against pain. The first period is also important, as well as the other periods. You also may.
What do you mean without effect?
Without treatment, it's first period, and sorry, yes, it's without treatment, yes. Yeah. Mm-hmm. And also, you may be interested in alternation of several drugs. For example, for pain disease, you may mix paracetamol and aspirin to avoid to improve the system. So you may be also interested in switching on treatments. So I mean that it's not obvious that there is a specific effect that must be the right effect. It depends on the context. But in this talk, we are interested in mainly in drug experiments and with effect of a drug which is taken constantly. So, for example, for two-period crossover design, you may replace the washout period by just putting the same treatment. You see, you have A, B, 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 and A. So in this period here, you have the treatment which is preceded by itself, so it corresponds to a real situation. And to be correct, the model must be, to avoid bias in the analysis, the model must be as precise as possible. So in this model, we assume that the response is given by the subject effect, period effect, but also a treatment, the effect of the treatment, DIG, which is preceded by DIG-1. So in the treatment applied to the previous period. So this is, in fact, the interaction between direct treatment effect and also the residual effect, that is the effect of the treatment preceded, which is applied on the previous period. And at the beginning of the experiment, you don't have any treatment. So it's like if you have treatment which is named 0 here. So 0 corresponds to having no treatment before. And here also you have some specific effect for having no treatment before. So in that case, correspond to the first time you take a treatment. So in that case, the effect of interest are CAA, that is treatment A applied on one period, having the same treatment applied to the previous period, and also CBB. But you also may be interested in the first the treatment effect at the beginning of the sequence of treatment, which is A0 and B0, or AB and BA, which correspond to switching the treatment. That is, for example, in that case, having treatment A, but in the period before having treatment B. Usually, if you want to replace washout period by a treatment, washout period usually are shorter. The interaction may include the fact that for this period of change, the period must be shorter. So this is included also in the model. What is the strong assumption of the model is that the carryover effect is no longer than one period. And also we consider that the period is long enough to have no correlation between observations. So now I will speak about optimal design for this kind of models. So the problem is the following. We have T treatments, number 1 to T, N subject, and K periods. And we have the full interact. No, sorry. We have the full interaction model here, the same as before. And in vector notation, we have B, which is incidence for block effects, P for period, and X is for full interaction between residual effect and treatment effect. In the following, we will omit period. Because the optimal design we will find with a model without period is the same as with period effect. So to obtain the design, we first remove period effect, but we can put the period effect at the end because the optimal design is the same. So, for example, for t equal to 3, the parameter of interest, this is the whole parameter which holds the interaction. I recall that 0 is having no treatment before. So you have t plus 1 entries of the vector C. And you have the vector of interest, which is phi, total effect, which corresponds to treatment having himself before. And phi is the linear combination of the whole parameter Xi by phi is K prime Xi, with K is S matrix here. Just for notations, for Xi, the entries are numbered with 2 indices. And it's the same for K. K here, he has for the row, he has 2 indices, and for a column, just one index. So below is for the row, and upper scripts are for the columns. So following the idea of Kushner in 1997, a design may be characterized by the sequence applied to each subject. For each subject, you have 1 second. For example, here you have 4 subjects, and for each subject, you apply 1 sequence here. And up to a subject permutation, you may characterize the design by the proportion that occur for each sequence. For example, here you have 4 different sequences. Each appears once, and therefore you have for these 4 sequences here proportion with 1/4. And for the other sequences that does not appear in the design, you have, of course, a proportion equal to 0. Of course, the proportion satisfies some constraints. The first one is that the proportion is between 0 and 1, and the sum is equal to 1. And the other one is that the proportion it must be proportional to 1 over n, because you just count the number of occurrence of a sequence over the number of total subject. If we release this last constraint, you obtain an approximate or continuous block design. So we allow the proportion to vary continuously between 0 and 1, of course satisfying these constraints here. So we have the set of exact design, and we want to find an optimal design, and as usually in optimization problem, you try to put this set of design in a continuous set of designs, which is the set of approximate designs. Now I will speak about the information matrix. First, for the whole parameter, which is simply like in block design, you have x prime d. This is a projection onto the orthogonal of the space generated by the block structure, and x. But we can split it into the sum of the sequence here, the information matrix for each sequence, multiplied by the proportion of its sequences, and also multiplied by n. So this is for an exact design. For approximate design, this the first formula does not apply because it has not sense, but we can apply the second one. So this is a general formula for the information matrix, exact design or approximate design. So I recall that CS is an information matrix just for one sequence of treatments. To obtain the information metric from the whole parameter xi to the parameter phi, we may use show complement, but it doesn't work in that case. So we prefer to use the extremal representation given by Gafker in 87 or extensively studied by Puckersham in 93. So we obtain the information metric for the parameter phi from the whole the information metric of the whole parameter here, just by this minimization problem. So we minimize over all the matrices L of size t plus 1 by t, satisfying this constraint here, and the minimum is obtained for the Loudon ordering. And since the minimum exists, we can have the same representation for the trace of the information matrix. So for the trace here, we have the minimum of the trace here. So we have put the trace outside the minimum into inside the minimum, and we can do this because the minimum exists and is unique. So we will use this exponent representation to obtain to derive optimal designs. So now I will speak about permuted sequences. So if you have a permutation of treatment labels and you have a sequences of treatment, then the permuted sequence S sigma obtained from S is obtained from S by relabeling the treatments according to the permutation sigma. For example, if you have the permutation sigma with two cycle 1, 3, 5, 2, 1, and 4 give 4, then from the sequence here you obtain the permuted sequence here with 1 give 3, 2 give 1, 1 give 3, etc., etc. So the notion of permutation was first the importance of such a permutation was given by Kiefer in 75, and then by Kushner in 97. We say that two sequences of sequence are equivalent if we can obtain one from the other one by a treatment permutation. So this is an equivalent relation. So we can group the sequences into equivalent classes. For example, for the design here, all the sequences are equivalent. We can obtain the second, third, and fourth one from the first one just by changing the label of the treatment. So in that case, you have only one equivalent class of sequences. And we say that design is symmetric if all the sequences that belong to the same equivalent class have the same proportion in the design. And Kushner also in 1997 introduced the notion of a symmetrized design. So from a design D, we can obtain a symmetrized D bar just by averaging over all the possible permutations. So if you average the design over all possible permutations, you obtain a symmetric design, which is a symmetrized design from D. So in our problem of optimization, now we have a new set of design, which is symmetric designs. And for each treatment D, we may have, for each design D, we have a symmetrized design D bar, which of course belongs to the symmetric designs. And in fact, we will find the optimal design not in the exact design, but in the symmetric designs. So I just recall quickly what is universal optimality. A design is universally optimal if and only if it minimizes all the criteria that satisfies the three conditions here. That is, phi is invariant by permutation of treatment labels, which corresponds here to a permutation of the row and column of the information matrix. Phi is non-increasing, and phi is convex. And this includes also, of course, the well-known optimality criterion, that's ID, E, and B optimality. So if a design D star has its information matrix completely symmetric, then necessary and sufficient coefficient to be universally optimal is that it maximizes the trace over all the competing designs, the trace of the information matrix. So now we have the proposition here that is for a symmetric design, the information matrix is completely symmetric. So to find a universal optimal design, you just have to maximize the trace of the information matrix. And also by concavity of the minimal representation of information matrix, we have that the trace of a design D is always lower than the trace of D bar. It means that the symmetrized design D bar is always better with respect to universal optimality than the design D. So now, and so the consequence is that D bar is better than D, and so we have to seek an optimal design among all the symmetric designs. So we have the problem here to find an optimal design in exact design. Now we change by seeking an optimal design among approximate design, and in this set of approximate design, we know that optimal design belong to symmetric design. So you may have outside, but if you have one optimal design outside, you have a corresponding inside. So we know that we have to seek optimal designs here. So that is that we will do. So in some cases, optimal design may also be an exact design. In that case, you can construct an optimal design, universally optimal design. In some cases, it's not the case. So you just use the theoretical approximate design to obtain efficiency factor of some exact designs. So I just speak about the groups involved in our problem. So from permutation of the treatment label, you may derive permutation sigma star on the carryover effects. And remember that for carryover effect, you have one carryover more, because at the beginning of the experiment, you have no treatment, which is equivalent, which is called a treatment zero. So you have a treatment zero here, and if you make a permutation of the treatment label, of course zero is still zero, and for the other treatments, you have that the sigma star is equal to sigma. So this is just to take into account that you have a special carryover effect for having no treatment before. And you also have sigma star, which is a permutation on the product set of 1 over t, so treatment labels and carryover effect labels. Okay. It's just a direct product group, that is a sigma tilde is of ij is a sigma I and sigma star j. And so you have that the permutation matrices here, p sigma star, which are corresponding to sigma and sigma star, and you also have p tilde sigma, which is a Kronecker product of p sigma and p sigma star. For example, for 3 treatments, so you have the whole parameter here, and the permutation p sigma p tilde sigma, which gives this one. That is, we make a permutation inside each block here, and then with the same permutation you permute the block between them. So you have here, you have a permutation here, and here with sigma, and you have also a permutation between the 2 blocks here with the sigma. Just to see this work, the relation between this work and the other works. So with Kushner in 97, we have K prime, which is identity and zero, and P tilde sigma, which is identity of size 2, Kronecker product with P sigma. Kunert and Martin in 2000, you have in that case is for a model with a left and right number effect. So you have identity 0, 0, and P tilde sigma is so the identity of size 3 Kronecker product with P sigma. In Kuhner and Stufken, it's the same thing, but for another model. It's a model when you had a special carrier effect when the treatment is preceded by itself. So you have also this structure here. In Blaise and Druilhet, we have this structure here. This is for total effect. So we have K prime, which is identity, and P tilde sigma, it's the identity Kronecker product with P sigma. And in Druilhet and Tenson, we have that it's for 2 left and right neighbor effects. You have for total effect, we have identity, and P tilde sigma is this one. In our case, well, the K is more complicated, but especially the group involved is more complicated, because you have P sigma Kronecker product with P sigma star. First, you have a star. That comes from the fact that we take into account that at the beginning you have a special carryover effect. If you use circular design, you just kit the star here, and then you have you have the corresponding group of permutation for circular design. But if you don't want to have a circular design, you have to put a star here. So this is more complicated, and especially what is more complicated is that instead of having identity the Kronecker product with P sigma, we have P sigma Kronecker product with P sigma star. So this is why it's a bit more complicated in the following. Don't recall that for design, the information for the parameter phi may be obtained from the information for the whole parameter xi by this external permutation, and the idea is to identify which kind of L may achieve the minimum. So we will call here L star. So we have here a technical lemma which says that L star is invariant when you apply P tilde sigma and P prime sigma here. This is for the column permutation of the column along according to sigma, and this is the permutation of the row of L according to tilde sigma. So the consequence of this lemma is that the entries of L star are identical when they belong to the same orbit of the group, and the group of the permutation of A j k, which is given by sigma I, sigma star j, sigma k. So you have here a group of permutation, and you know that L is constant on the orbits of this group here. If you have a circular design, you just remove the sigma, the star here, and you have just the triple orbit of the group, but here it's just a bit more complicated because of the star here. We have 7 orbits in the group. All the entries equal to 1, equal. The 2 first entries are equal, etc., etc. The 5 first orbits, it's for inside the design, and the 2 other one, 6 and 7, it comes from the fact that you take into account the a special carryover effect for at the beginning of the experiment. So, for example, if you circular design, you just have 5 orbits and not this one here. So, since L star is constant on the orbit, L star may be expressed like that. You have it's a linear combination of LU. Well, LU for the orbit U is a matrix which is 1 if the entry belongs to the orbit and 0 if it doesn't belong to the orbit. So we call this L gamma. Just it's not written here, but the L1, if in fact is equal to K. Just a remark. And the constraint here with L star prime K identity, which is this constraint here that must satisfy L star, implies that gamma 1 is equal to 1, so gamma 2 is equal to 0. So you have 5 free parameters and 2 which are constraints. The first one corresponds to 0, the second one to the first one to 1, the second one to 0. So you have to optimize among 5 parameters. So we want to optimize the trace of the information matrix. So we just apply the formula here with L gamma instead of L star. And so this is a minimum in gamma just when the 2 first are fixed, the first one with 0 and the second one with the first one with 1 and the second one with 0. So it's a 2-degree polynomial with 5 variables corresponding to sequence S. This is the trace of this information matrix here. So we have that the trace of the phi is the minimum over gamma of the proportion PDS and this quadratic function here, which is a convex function. So we want to obtain the optimal design, we want to minimize in gamma and maximize in the proportion here. And since Q is a convex function, is not it can be handled computationally. It's not so difficult because you know that you have one minimum, and by convexity it's easy to find optimal design. So now I will show some example of optimal designs obtained by exact calculation. I use Mathematica to obtain exact proportions. For k is equal to 3, that is, you have 3 periods in the design. The 2 optimal sequences are 1, 1, 2 and 1, 2, 2. When the number of treatment is 2, the optimal proportion has 1/2 for each sequences, and so on. For example, for t equal to 4, you have 1/3 of the first sequence and 2/3 of the second sequence. So for k equal to 3, t equal to 4, and n equal to 36, you have this design, which is an optimal design, universally optimal design among all possible designs for a model with a full interaction. For t equal to 4, the optimal design is generated just by one single sequence, which is 1, 1, 2, 2. So for t equal to 4, you consider all the possible permutation, and you have here an optimal design. Just say that the column has the row as the periods, and the column as the subject. It's not the same as the previous. And for k equal to 5, you have this proportion here. For t more than 5, I don't wish to have exact proportions, just have numerical proportions, but I don't know if I can fix this problem or not. So you have two optimal proportions, 1, 1, 1, 2, 2, and 1, 1, 2, 2, 2. And here are the optimal proportions. And for k equal to 6, you have these two optimal sequences and with the related proportion. Okay, so I have finished my talk. Thank you very much.
Thanks very much, Pierre. Well, are there questions or comments?
Usually, when I come across these things in the literature, they have two periods. I mean, clearly you can't estimate very much, but often people seem to run designs with very few periods.
Yes.
Yours are bigger, of course.
Yeah, but usually they use washout period,
Yeah.
which corresponds for four period design, and this corresponds to this kind of design here. It's the same as the beginning. From this, in fact, in that case, what you observe is the effect of a treatment which is preceded by a washout period. But when you use a drug, you don't use a drug, then you have a washout period, you use a drug and washout period, you use it constantly. So perhaps in that case, we have to see from a medical point of view it's relevant or not. But in that case, perhaps it may be to have 1, 1, AA, BB, and BB, AA. This is a 4-period design. In that case, you have the same efficiency factor. This kind of design may be more efficient than the previous one for the effect of A preceded by itself, because you obtain the structure of the previous design here with this 4 here periods which correspond to the first. But you had here treatment. That is, you may also estimate the fact that the treatment is not preceded by itself. You can compare it if it does really has an effect. You can compare this here from this here, which is the effect of a treatment which is preceded by itself, and here it's a treatment preceded by nothing. You can also estimate the switching effect of treatment, so you have more possibilities. And for here, when you want to estimate this effect here, you have the same structure here, but here in this design you had more observation and more parameters. So you don't lose or gain efficiency, but you may estimate more parameter. And especially what you are interesting here is that this effect here, which is not the same. Here the effect is a treatment which is preceded by itself, and in the previous it's a treatment preceded by a washout period. In this kind of design, you may also estimate if there is, you can consider here as a washout period, you can estimate if there is, you can test if there is a difference between this effect here or this with this effect here. And if there is no difference, you can gain in optimality because you have twice more observations.
Thank you.
But let me discuss with medical.
Vladislav?
So the universally optimal designs, the exact universally optimal designs that you showed us, these happen to be approximate universally optimal designs, right? In the same time,
yeah.
simply in that intersection of the two sets that you showed us.
Yes, wait.
So for these numbers of n, k, and t, for very special numbers of n, k, and t, it is possible to construct such exact designs. Am I right?
Yes, yes. For example, here,
Here.
for this one.
Say yes.
Yes, you can obtain, but of course, if you have 35, you don't have optimal design, but you can calculate efficiency factor, which may be interesting.
Yes.
Because you have a
Yes.
short
Yes.
efficiency factor.
I know. So, for example, if you have some different n, say 31, of course, you wouldn't be able to construct a universally optimal design, but just using some numerical procedure, for example, heuristics, say, you have some benchmark
Yes.
to compare these
Yes, exactly.
resulting exact designs, and say if it shows that it's 95% efficient, then
Yes.
you're all right with your heuristically found design.
Mm.
So these efficiency factors, of course, are important and useful.
Yes, absolutely.
You were assuming in your crossover situation that the carryover effect or the interaction is just span, how you call it, covering one period.
Yes.
And,
Yes, this is the stronger assumption in this
Yes, I think
design.
so.
Yes. Yes.
This example.
Yes, this is the stronger assumption is that we assume that the treatment effect, well, the carrier effect is no more than one. Oh, sorry, it's not this one.
The design that you just showed us.
Well, it's written somewhere, I don't know. Yes, the carrier is no more than one. This is a stronger assumption. It's the same when you use a washout period, because when you have a
Yes, of
2x2 crossover design, you assume that after washout period you don't have a carryover effect. If you have one, then you lose a lot of efficiency of the
You
design.
can check whether the washout period is effective, and then your model applies. But in this case, you cannot do that, is it? You cannot check whether the assumption is effective. If you show the
Yeah, for 4x4, because from a 2x2 period crossover design with washout period, you can have a 4 period design. If you use more period, you can estimate it, because, for example, here, normally the effect here is the same as here. If you are under the assumption that the carrier effect is no more than one period. But you can also test, because you can also have a more complicated model, assuming that you have a two period carrier effect. In that case, you can test, because you can test this against this. This is having just one carrier. Oh, for example, here you have the carrier effect of this one here. This is carrier effect of this one, and this one normal under the assumption with just one period carrier effect, it must be the same, but you can test it. You have the same here and here. So you may assume, but you need longer periods.
I have a comment, if I may. I'm glad you've got this slide up here, because lots of your optimal sequences just have two things in, and in that case I think you really do have to apply the whole symmetric group. But the thing which you managed to lose before, if you've got three things in a sequence, then this is something that Pierre and I discussed in Tomar, wasn't it, a year ago. If you've got three things in a sequence, you don't actually have to apply the whole symmetric group. It's enough to get something which I think might be an orthogonal array of type 2. Anyway, you get all triples which have the property that in every two adjacent places all possible ordered pairs come. And you can do that in t times, you can always do that with just t times t minus 1 triples. You don't have to go up to any further. We've got methods that definitely do that. So of course Pierre asked me about it in general, when you might have more than 3 things in there, and my general methods have some holes in for bigger values of k. But if your method means you never need more than 3 different things, then I'm quite content, because that stuff that I've written down for you, which we've now both carefully kept a copy of, will definitely do 3 different values for all possible values of t. So it always seems to me when you're using Kushner's method, there's 2 things. One is I just find it incredibly hard, even though I've managed to write a paper on it. Didn't we, Joe?
We did.
We did, yeah.
Yeah, but there was a small error in it.
Well, I'm not surprised. I'm not surprised. I can never quite get my head around the maximising and the minimising and what's actually going on. But his method essentially says, well, we apply the whole symmetric group. And what I'm saying is, although that's a nice way of conceiving it, for making designs in practice, you can often get away with a smaller collection of triples or whatever that have the right combinatorial property, and so you've got more chance of actually getting an exact design without having to have little n be some huge number.
In fact, it's related with some orbits of groups. So
No, it isn't. It isn't necessarily. No, some of these things don't come from groups.
because when you act in a group, your special tricks that you can achieve, not with the whole group, but just.
These don't all come from groups, actually. Sometimes they do just come from 2 transitive groups. But I think that the one for 6 doesn't. It comes from a rather special Latin square. So although I like thinking about it in terms of groups because that's my background and the algebra is nice.
Yes, this applies very well with this kind of group here. But with this one, I think it will be a little more complicated to handle with. With this kind of group, it works very well. So you can reduce actually the number of subjects. Yeah. But with this one, we have to think more, because it's not so
it's not
exactly the same case.
No, exactly, because we've got that extra complication. Sorry, I'm taking over Pierre's stuff. Anyone else?
Well, you're assuming here that all the parameters are of interest, is that right?
No, just total effects. The other may be a secondary, but the main parameter of interest is this one here.
Just that much? Oh, okay, that's right. So all the others are treated as...
It means a treatment which is preceded by itself, because for the
all the others are treated as
Newton's parameters. Yes.
Okay.
And perhaps I could put in there, Pierre gave 2 different contexts, the sensory one and the disease one. The context that I come at this thing from is actually agricultural field trials and neighbour effects. And if you're trying several different varieties of sunflower to see which one you're going to recommend to farmers to grow, what the farmer needs to know is the total effect. But when you've got these things on small plots in the field, different varieties may affect the ones next to them. And so what Pierre is doing what he described here would be in the rather special case that the neighbour effect is only from one side. which happens, I mean, we had one stuff on sunflowers of different heights, and we were worried about the effect from the south, because, you know, that's where they would be shaded, and we didn't care or worry about an effect the other way. But sometimes for field trials, you've actually got to play this sort of game with effects from both sides. So in doing the experiment, you have to worry about the neighbour effects, but in thinking of what you're going to recommend to someone, they're not going to be growing a mixture of sunflowers in their field, they're going to just be growing one lot.
Yeah, we can adapt this technique with the two-sided neighbor effects, but it's more complicated. You have more orbits, but we can do it.
Anyone else? Well, thank you again, Pierre, for a very stimulating talk.